Okay. One of the most well-known direct couple multi-stage amplifier is Cascode amplifier. So Cascode amplifier is the combination of common emitter with a common base. This is combination of common emitter with the common base. So this arrangement provide high input impedance but a moderate voltage gain. So high input impedance and moderate voltage gain. Okay. So we have discussed in the previous class the motivation or the reason why we need to have the multi-stage. So we want to have the multi-stage. There's several reasons. One of the reason is the impedance. So we want, for example, we want to have a very good voltage amplifier. So for that case, we need to have the high input impedance and low output impedance. Okay, in terms of the gain, we need to have the high voltage gain. Okay, and another reason or motivation why we want to design the multi-stage is we want to obtain an amplifier with wider bandwidth or high cutoff frequency. Okay. So the Cascode amplifier, the features or the characteristic of the Cascode amplifier, one of the main characteristic is the high frequency, high cutoff frequency, which is high cutoff frequency. Okay. So when we use the single common base, if you use the common base, this is common base. Common base is a configuration that give high voltage gain. Okay, so this is good. So common base has a very good characteristic in terms of the voltage gain because it offers a high voltage gain. Okay, however, the common base has a very low input impedance. So this is not good. Okay. So this is why we connect the common emitter. Okay, common emitter in front of common base. So common emitter in front of common base. So common emitter will provide much higher input impedance. So the input impedance, this is common emitter. The input impedance is not so low. So we have a acceptable input impedance. So CE is ZI okay. Okay, ZI okay. And then one of the, as I mentioned just now, the Cascode amplifier allow the amplifier to operate at higher frequency operation. So this is because when you use the common emitter configuration, so the high cutoff frequency is limited by the capacitance, by the what we call it a Miller capacitance. Okay, so we have learned in the chapter BJT, when we calculate the high cutoff frequency, we need to convert the feedback capacitance. For this, for the common emitter, the feedback capacitance is the base collector capacitance. So the feedback capacitance is converted into the CMI and CMO. So the CMI will become very, very high. The effective capacitance seen at the input is very, very high. So this is the multiply by 1 minus AV. So at the end, the CMI is high. So when the CMI is high, the high cutoff frequency value will become lower. So means that it cannot operate at high frequency. So how we can increase the high cutoff frequency is by decreasing the input side of the capacitance. So the way we can decrease the CI here. CI here is we can decrease the CMI. So how we can decrease the CMI is by decrease the AV, voltage gain. So in the Cascode amplifier, the voltage gain is approach the unity. So the voltage gain of the Cascode amplifier is almost equal to -1. So in this case, the CMI will be minimum, and the input impedance, input capacitance will also become minimum, and the FHI will increase. Okay, so this is the characteristic of the Cascode amplifier. Okay, so next we do the AC equivalent circuit at the mid band. So we start from the input port. At the input port, we have the RB1 and RB2. Let's say this is RB1, RB2. Okay. Base and emitter, we have the R pi. This is R pi 1, and this is the V pi 1. At the collector, we have okay, note here is the bypass, so there is no RE. Okay, at the collector and emitter, this is GM V pi 1. So this is the RC. Okay, this is the first stage. At the second stage, this is a common base. Okay, so please take note that for this example, I'm using the PNP. This is the PNP transistor. So the current flow is in this direction. So the PNP hybrid pi model, from the emitter, this is the R pi. Okay, this is the emitter, this is base, and this is collector. This current direction will pointed to the right hand side. So the V pi will be like this. So the current of the base is towards the downward. So V pi plus is up at the up. So this is a PNP. Okay. So we can use this one. So this is the R pi to V pi to, this is GM to V pi 2. At the collector is connected to the RC. Then now we have the output port. Okay, so this is the AC equivalent circuit of the Cascode amplifier. Okay, for the Cascode amplifier, actually we can use the both NPN. So if in case of both NPN, the proper the way we draw the hybrid pi model is slightly different. The difference is in terms of this GM2 V pi, GM V pi current direction, and this V pi polarity. So if I draw the NPN, so this is base, this is R pi, the polarity, and the current direction is collector, emitter, GM V pi. So this is NPN. Okay, for the example, after this we will use the NPN. Okay, so this Cascode amplifier. So from the AC equivalent circuit, we can characterize, we can investigate or determine the input impedance as well as the output impedance. So the input impedance is straightforward. The ZI is equal to RB. RBB1 is actually referring to RB1 parallel with RB2. So this is RB1 parallel with RB2. So Zi is RB1 parallel with RB2 parallel with R pi 1. Okay, for the output impedance is equal to RC. Okay, for the voltage gain for the multi-stage, we can analyze the voltage gain at the first stage and the second stage. AV1 is the voltage gain at the first stage. So let's say we label the input voltage here. This is VI. The output voltage at the first stage is labeled as the Vout1. Okay, so this is Vout. So AV1 is Vout1 over Vi. So this is equal to, so Vout1 is the voltage drop at the RC parallel with Zi2. Okay, RC parallel with Zi2. So what is Zi2? Zi2 is equal to the, so this is the Zi. Zi2 equal to the Zi impedance seen from the emitter port. So this is equal to R pi 2 over beta 2 plus 1. So this is equal to R pi 2 parallel with over beta 2 plus 1. Okay, so the Vout1 is equal to, the current here is minus GM1 V pi 1. So minus GM1 V pi 1 times RC parallel with Zi2. Okay, this is Zi2. Okay, this is Vout1. How about the Vi? The Vi here is equal to V pi. So cancel out the V pi, so you can get the AV1. Okay, for the AV2 is equal to Vout over Vout1. So the same analysis, the Vout1 is, Vout is equal to is GM2 V pi 2 times RC. So this is GM2 V pi 2 times RC, and then the Vout1 is equal to V pi 2. Cancel out, so you will get the equation for AV2. Okay, lastly, the total equation, total voltage gain for the multi-stage is the multiplication. You multiply the AV1 with AV2. AV1 times by AV2.